Okay, so now we're going to get into the building envelope. We have our foundations, we have our site work, and we've looked at general conditions. So now it's time to get into this. And obviously, the first role that a contractor plays on a green project is to get a well-built envelope. This is critical. An average new home has 4 square feet of penetrations equivalent to an open window. So every time you and or your subcontractor comes in and puts a penetration in the wall, keeping control of that and making sure that it doesn't allow air infiltration later is a really critical strategy. By doing this, the green contractor can add about 10% on average overall efficiency to the building project. That is incredible, and that's worth a lot of money if you think about a large building. One of the things that we want to worry about is that we want to have certified lumber. Now again, this has less to do with building efficiency, but more with greening or being sustainable, thinking about where the wood comes from. And saving lumber, being resource efficient. So for the architects, do you need an 8-foot wall or a 10-foot wall? I'm not sure what the metric equivalent is in Europe, but you know, wood in this country comes at certain dimensions, and if you can maintain those and still get the proportions that you want, that's a very effective strategy. And certainly going from 16 inches on center wood studs to 24 inches on center wood studs is not only going to save you a lot of wood, but it's going to reduce your thermal bridging, which I will come back to later. And so one of the big things now I'm going to talk about is exterior insulation. Is where does your insulation go in the wall and why? We're going to get into that right in a minute. So building wrap being one of the first things. You know, building wrap is something that's more and more being used to protect against moisture and also to make sure that your building is airtight. And sometimes we wonder about having a building that's too airtight. So for example, my son had some breathing problems when he was young. He had a little bit of asthma, and we lived in a house that leaked like crazy for air, and we always had fresh air in the house. So, you know, there's always a dilemma between having fresh air and having clean air and having a building that's super efficient, super tight with air that kind of doesn't move back and forth. So, you know, that's really a tricky thing that we need to think about, and we're going to keep going forward here. So I'd like to ask you, if you're watching this video, which of these is more sustainable, the wood studs or the metal studs? Wood studs can be renewed or regrown, meaning that there is a renewable stock available, as opposed to metal, which is a non-renewable stock, although there's a lot of metal. However, metal studs can be recycled. Wood studs, not so much. Wood studs are easily worked with multiple trades. People seem to know how to use it, whereas metal studs are a little bit newer to the residential construction market especially. Metal studs already have holes in them to allow wiring to go through versus wood studs, which has to have holes put in them. What else? Wood studs can come from sustainable forests. That's a good thing. And the other thing is that wood studs are sequestering carbon from years ago, and instead of a tree being chopped down and burned or put into a landfill, that wood's being stored in a building now as structure, and therefore is sequestering the CO2 for hopefully 100 years. So the answer is not clear, wood or metal, but certainly what sustainable designers and builders are always doing is debating that depending on the project, one or the other will make more sense. It's up to us to kind of work with the client, the builder, the architect to try to figure that out. Now, R value, of course, is a critical aspect of when we think about sustainable envelopes or green envelopes. In this country, we use R value and U value. In other countries, U value is it. R value is the inverse of the U value. It measures the material's resistance to temperature or functional flow. And the higher the R value, the better. It doesn't necessarily mean you have a great wall when you have a lot of R value, but it does help. What we want to try to do is block out thermal bridging and make sure that temperature is not moving through the structure of the building into the house to try to keep it cool. Now, thermal batten insulation is typical. However, fiberglass more and more is being questioned, not questioned, but certainly has some issues with, how do I say that? I'm trying to be polite because I think it's a great material. However, you'll notice that more and more guys or gals are wearing respirators or at least masks to block some of the particles. We definitely want to reduce particles getting into our lungs. However, it's a very cost-effective material. And unlike this material, which is really great, I don't know if it's quite that soft. I've used this product in my house. This product's more expensive, made from recycled blue jeans, and has a great feel to it, and is an alternative to thermal batt insulation, absolutely. Now, if you don't install the insulation properly, it doesn't matter, especially up here at the top. This is where things kind of go wrong. if you leave an air gap in the insulated wall, you've kind of defeated the entire purpose of spending the money for that insulation. Your other option, of course, is spray foam. Now, the debate is out on spray foam. It has some petroleum products, some other chemicals, some VOCs, so there are some that shy away from this. But one of the great things about spray foam is that it both, well, it gives you R value, and it also seals up all of the air leakage in the wall. So therefore, very effective. Now, the low VOCs, low formaldehyde versions are great, more expensive, of course. Over time, the prices for this should be coming down and are coming down. Now, one of the other great strategies, though, is to use rigid foam insulation on the outside of the building. And this is really probably the key strategy that I see out there. I mean, I love foam, but if I had the choice between foaming between studs and using rigid insulation on the outside of the building, I'll choose the rigid every time. The energy models bear this out. Essentially, the rigid insulation is providing a thermal blanket for your building and blocking thermal bridging. So it's an amazing way to keep your building sealed off and insulated. And if you happen to have masonry on the inside of your building, then you have an opportunity for thermal mass and thermal lag to help with your HVAC system. And it gets, roughly R5 per inch. Typically 2 sheets is what you'll see. There are more and more newer products that are not only just putting up exterior insulation, but zipping up the joints between it to really create a nice point. And in some countries, you'll see SIPs, which are pre-built panels that are particle board and basically foam with the wood stud only every 4 feet on center at the end of the. And the problem here with these walls, of course, is as you begin to puncture them with holes for electrical, plumbing, mechanical, etc., they start to lose their integrity and they start to not be as good as they are advertised as. So if you intend to want to use these, you need to make sure that you have a really good sense with the subcontractors of how to penetrate those walls. Pretty critical. Now, I'm a big fan of alternative construction. One of the big ones right now is straw bale. This is a project I had the opportunity to work on with Revision Architecture. That is a straw bale wall conference room. Notice that, for example, you have to educate your local codes. We had to build a wall and burn it in front of the code guy to make sure he knew it was a 2-hour wall. Rammed earth is another opportunity that you see more and more. And one of the things I want to point out here is you have a very high foundation wall. So what's happening is that if it snows, there's no water getting into this. And then a pretty good overhang. You probably want to have as much of an overhang as you can get in order to protect that straw. And that straw will be covered up with plaster, by the way. That plaster can be found on site or can be purchased. Now, thermal bypass is really like thermal bridging. It's really a key aspect to making sure that your house or building is energy efficient. So sealer and flashing between the foundation is critical right in here. This is where you get a lot of leakage there. You get some leakage there. Caulk bottom plate. So there's a lot of caulking that's involved to really keep that air out. Air seal the joint cavities between the floors and other kinds of things like this, for example. This is really a key strategy. I know these might seem obvious to you, but there are plenty of people that are not doing this and therefore compromising the work that they're doing. And so caulking around all of these outlets is really pretty critical. Block and seal cantilevered floors and knee walls. Cantilevers, of course, are great, but they bring opportunities in for air infiltration. Weather stripping is key. Watch your knee walls. Insulate caulk or foam between window and door jambs. That's obvious, you would think, but doesn't always happen. And certainly recessed lights that go up into the attic that has exposure to the attic are really critical to get the right lights that actually have a dome over them to protect against air movement between the attic and the living room. All of these, by the way, will lead to a situation where your house is going to be, again, 10 to 15% more efficient. And obviously, as ducts move in and out of the attic into your house, you have to watch out for that. Fireplace is really a big no-no for sustainability. I know you think, well, that's a free, biodegradable and renewable stock for energy, but they're not really efficient for heating, and they tend to draw outside air into the house. Did you want to get it for aesthetic value? Maybe. Okay, so for U value, low is good. In this country, we use U value for windows, and it is the inverse of R. So if you have a U value of 0.25, 0.25 goes into 1 4 times, so your R value will be 4. If you have a U value of 0.33, your R value will be 3. If you have a U value of 0.5, your R value will be 2. And it's a measure of how BTUs, British thermal units, transfer through, for example, in this case, a window, through conduction. It's a measure of the rate of conductive heat loss or gain through a material or assembly. R value and U value are essentially two sides of the same coin. And why in the US we use both, I don't know. I wish we just go to U value. I think it's more descriptive. Low E coatings, amazing invention. 20 years ago, we would say, should we use low E windows or not? Now, standard low E windows are standard now for any project that has any kind of decent budget. And that is a clear liquid sort of formula that gets placed onto the window that gives it some performance for solar heat gain coefficient, which I'll talk about in a minute. Solar heat gain coefficient. So SHGC measures how well a product blocks heat caused by sunlight. Especially when you have tinted glass, the solar heat gain coefficient will go up and be better. And so we want to know, when we buy windows, we can begin to think about that solar heat gain coefficient. And that's really critical for energy modeling, which asks for all the properties of your windows, your U value, your solar heat gain coefficient, etc. And so here's your solar heat gain coefficient, your U factor, and some other aspects of the windows. Now, visible light transmittance is critical in a sustainability project because you want daylighting. And so in order to do that, you may sacrifice some energy efficiency in order to get more daylighting into your building. And so the higher the VT, the more light is transmitted, and we want to maximize daylighted. VT value is usually between 0 and 1. And this is really, as you'll get more and more into sustainable design, you'll see this as a really critical factor in how you're selecting your materials. And finally, for the envelope, we're going to look at roofs. There's a term called solar reflectance, which is the ability to reflect the sun's light and with it the heat back up into the environment. That's a good thing. We might call that albedo or a high albedo material. So that might be something that might be called white or some light material. And in the cities, what we can do is if all of our roofs were white instead of black, we would reduce the overall ambient temperature in the city greatly. And so the move is on to go to all white roofs now anywhere that you can, or especially a green roof, which would be great. And thermal emittance is a little bit different. That's the ability for a material to absorb and then emit the heat back out into the atmosphere. It's kind of a complex physics assignment there. When you think about both, you want high. When you think of them together, you'll see reflectivity and emittance. When you take those together, there's a weighted average that generates an SRI. And so when you're selecting a roof material from a sustainability point of view, you're looking for a high SRI and not a low SRI. Now, skylights are a big no-no in sustainable design in general because of heat gain and heat loss and glare. We tend to prefer clear stories and roof monitors, ways to bring in light up high. We do want to do that, but have a vertical panel of glass there so we can shade it and or bounce light through it. So there's a problem there. Roof monitors or clear stories are really the way to go, and we tend to look at those. And if you look at sustainable projects, you'll see that quite often. I kind of like the solar tubes. I've used them many times on projects. I think they bring in a consistent daylight that reduces the need for electricity for artificial lighting. And then, of course, there are the green roofs. Now, if you're in the middle of nowhere where there's no buildings and it's all trees and forest, if you were to do a green roof, that would be pretty dumb. The main purpose of a green roof is to control the rate of peak runoff. It's not necessarily to bring habitat into the environment or to create a good view. It really is about controlling the rate at which stormwater leaves a building. And it does that through transvaporation, meaning that some of the moisture, when it hits this, evaporates into the sky. It does have added benefits. Reduced heat island effect, for example, just like a white roof. An increased life of roof membranes, so it'll protect your EPDM roof. And a couple other things that it will do is that it will create habitat, as I said before. It will also help with your heating and air conditioning. Saves 5%, but only on the top floor. So when you hear vendors say, use a green roof, it'll save 5% on your heating and cooling. Yes, if you have a one-story building. If you have a two-story building, it will not save 5%, it will save 2.5%. So you have to be really careful when you're a sustainability expert to really read through the materials carefully and understand what is going on. So that was building envelope. And now next we're going to be moving into interior finishes.